Okay, welcome back. We have two important conservation laws to demonstrate, to complete the set of physical laws that are important in ideal fluid mechanics. One is energy, kinetic energy for fluids, and the other one is helicity. It's remarkable that the conservation of helicity was done recently. By recently, I mean historically recently. So in the last 50, 60 years. And is quite surprising because fluid mechanics has roots in 18th century, and so one would think that maybe by 19th century all major conservation laws had to be found, and very interesting. And of course I'll comment on that as fundamental invariant at the end of today and tomorrow and the following day. So I will reserve more time to this last invariant, helicity. But of course energy is also important, and relationship between energy and helicity are very important for a number of reasons. And so I will dwell on these aspects more. So let me talk about energy for classical fluids. I will be, as time is short, I will constrain myself to very, very simple case. So of course energy means everything in physics, and I will immediately say that some contributions to energy will be neglected, either because they are very, very small compared to the motion of the fluid, for instance, internal energy, enthalpy, etc., etc. If we interpret enthalpy in terms of pressure, that we can do, of course, that is important. Otherwise, I want to duel, of course, with a contribution from molecular motion, and as similarly for energy due to other aspects. For example, heat transfers. As far as I'm concerned, I won't consider heat transfer. So our fluid is really, in a sense, adiabatic from first principles, by assumption. There is no heat flow going from one region of the fluid to the other. And of course, if we want to consider that, which is clearly very important, it should be considered as well as dissipative effects, etc., etc. So this fluid is so idealized we can call it an isentropic fluid, entropy constant. And of course this contradicts with fundamental principles of physics, and we are aware of that. And when it will matter, maybe not during this course, but when it will matter, then of course we have to take care of these effects. By the way, I won't talk about changes of topology, but when changes of topology occur, as I mentioned yesterday, clearly an important issue, there is an energy exchange, and that is due to, in classical physics, is due to the dissipative effects, but it may be due to heat flows, etc., etc. So when we include these effects, then of course the fluid is no longer isentropic, and we need to take care of this. All right, so under these assumptions, so simple, the energy that we care about, or the bulk of energy that is relevant for this type of fluid, is kinetic. So kinetic energy, motion of the fluid. And you understand immediately, if you think of just human experience, that on simple human experience base, we understand that kinetic energy is by far the amount of energy that matters in our context. Now, so I will skip details, and I want just to prove to you that kinetic energy is usually defined in this form. We have the velocity of the flow squared in the volume, and this is the volume we consider V, and this quantity is conserved under ideal motion, Euler equations. So we will use Euler equations to just demonstrate that the total derivative with respect to time of this quantity, kinetic, is conserved. So indeed, this 0 means that kinetic energy is a constant. Constant is a constant with time. All right, so this can be done quickly. d dt of what we have there, a half u squared d3x, and this is just a half. We have, actually, I should have put here the density rho, fluid density rho, so is half integral of rho d dt enters in this integral. Remember what we did yesterday, okay? And so we have just standardly this v of rho u du dt. Now, du dt has to come from Euler's equation. And yesterday we saw Euler's equations in terms of du dt. Remember, Euler's equations are the conservation of linear momentum. Okay, so du dt, do you remember what it was? Minus, there was a rho here, minus grad p, okay? So mass times acceleration equal the force. And the only force we consider here is pressure. Then you may add conservative forces. You still call them Euler's equation, although we are not considered by Euler, but it's an easy extension. And if you add dissipative terms, heat flux, viscosity, etc., these become Navier-Stokes equation. Okay? So this is a little exercise to keep in mind these equations. So if you don't remember these equations, just take your time and think. You use Newton's law. Mass time acceleration equal a force. And then you think of your situation of a fluid, etc. You come up with that. Okay, so we have to substitute this here. So we have rho du dt here, and we have a grad that comes inside. So d kinetic in dt is just u. And then if I consider, you remember we considered conservative forces, then I can put something like a potential there. I can redefine my potential as chi, say minus p plus phi. And then I have there a grad chi. Okay? A grad chi d3. And, okay, so this is just the volume, the integral on this quantity. Chi, I take chi at infinity as a reference, d3x, and under the assumption that, well, I can consider incompressibility, incompressible fluids. Then div u is equal to 0. Okay, so we have d is just simplifies this demonstration. dt is equal to the integral. If we take this, then it's easy to put it in this form. U times the chi minus chi infinity. It's just a reference value to infinity. And this is d3 dx. And so because this is the operator we care about, we transform this into, as usual, into a surface integral. So we have u nu, the normal, to the boundary of v being s. And this is times chi minus chi infinity in d2 x. And this is 0, especially in the case where we consider an infinite domain, or where at that infinity, so to speak, the value of chi just gives 0 to this integral. Okay, so this is conservation of kinetic energy for an ideal fluid. And now we are done with the classical equations. I'd like to go back to a little point. We talked about Lagrangian and Eulerian reference. And I'd like to remind you of, we started everything considering a flow map. And the flow map from a point x0 to a point x at a later time. So time is working here. And the flow map sends any point at the position x0 initial to the x final. This flow map is what is behind all we're doing. Remember, we assume this flow map is smooth. It admits an inverse at all times. So we are constraining ourselves in a particular situation. Under these conditions, we can consider the Jacobian of the transformation. Any element of volume element is going to be transported by the flow and is going to change shape continuously. So we can define the Jacobian. Now the Jacobian, I will denote the Jacobian as x0, just to remember that is a matrix that takes into account the changes of one variable, of one vector with respect to the other. So in particular, by J, if I underline it, if I were to underline it, it would be a matrix. You remember dx on dx0, etc., etc. So it would be a 3 by 3 matrix. dx, dy, dz with respect to x0, or the other way around. This would be dx, dy, dz, dx, dy, and dz with respect to y0 and z0. Okay? And now, if I underline it, is in a matrix. If I leave it like this, is a determinant. So I consider this as the determinant. Sometimes is written like this, dx over dx0. Like this. Okay, so this denotes the change of an element of volume from the initial position to the final position, and from linear algebra. This is just an exercise by doing derivatives inside this matrix. One can show that we have the following: dj over dt is equal to j dv. You just apply derivatives inside here and you construct your equation. This is just purely algebra. Now, the same, if you pay attention to what we define as the continuity equation, well, the continuity equation, the change of rho, of density, of fluid density, continuity equations obeys the same equation. So it's the first conservation law we introduced, based on the principle that mass is conserved. And so the structure of that equation and this equation is the same. So if we consider a particle trajectory, so if x is thought to be a particle trajectory, then we can say from the initial time t equals 0 to a certain time, we can interpret this equation on a material line. On a material line, the Lagrangian derivatives becomes ordinary derivative, and so we can consider this or reduce this to an ordinary derivative. Remember, we stay on the particle trajectory for this. And so we can reduce this or interpret this as just a standard derivative, d dt, etc., j dv. And so we can integrate that, and this means that on the particle trajectory, we have a function j x 0 that goes like exp to the integral from t equals 0 to some time div u in dt. All this to tell you, remember, their incompressibility, we use it for simplicity. For simplicity, we use incompressibility, and that is the condition, div u equals 0. Not necessarily. A fluid can be compressible. And you see that equation, that condition compare is just shown up there. Is just shown up there. And what that means? It means that if we are in an incompressible fluid, the Jacobian of the transformation is equal to 1. So this is another way to state the same concept. Either div u, divergence of u equals 0, or Jacobian equal 1. Okay? So we can now resume these various facts into the following. By the way, because we stay on a material line, we can multiply this. This is again a little exercise showing. We can show that indeed, rho j is constant on a particle trajectory. And this is also a little remark, d dt of rho j. Okay, we perform just derivatives here. Okay, the rho dt j plus rho dj dt. We convert this in a Lagrangian form, and we use the usual condition. The rho dt comes from continuity, so we have minus rho div u from continuity, and then plus the other one, rho, and this dj dt comes from the Lagrangian form, same thing, and so we have rho j div u, and this is exactly 0. Okay, so we can state the following statements. The following statements are equivalent. One statement is that fluid is incompressible. Oops. Okay, fluid is incompressible. It means that del rho dt equals 0. Then, just a last summary of all this notation, that the divergence velocity is velocity field is solenoidal. And the third being this last information that fluid flow is, as mathematician says, volume preserving. Okay, so you now have three ways to mean the same thing. So if this, I wanted to say because sometimes, actually very often, you may run in papers of a more mathematical or more physical context, and you may wonder what they mean, volume preserving or solenoidal. Of course, you know better solenoidal. Volume preserving flow is Jacobian equal 1 is incompressible. So there are pure mathematics paper that consider divergence-less fields. And this is talking to you, to physicists as well. Solenoidal fields, oh, okay, I understand what they mean. Or volume preserving. Volume preserving was... Okay, so we've done with this. I'm tempted to use the Jacobian. I'm pretty sure you did this in the basic courses of calculus. Use Jacobian for change of coordinates. You may remember that. Is one of the exercises that give you when you do integration. And so sometimes you wonder, what is this Jacobian? This Jacobian is exactly, in fluid, is so evident, is a volume that may or may not undergo changes of, through deformation or through changes of volumes. So if the volume stays the same, then the Jacobian is 1. It doesn't mean that the volume may be squeezed. It may deform, of course, and that is the role of the Jacobian. All right, so through this Jacobian, you can also demonstrate, this is just a piece of math, you can also demonstrate the kinematic transport theorem. Instead of, you go from the initial position to the final position, you apply derivative, the Lagrangian derivative, to that integral where you have this volume V, and I'm tempted to do it, but I would like also you to do the exercise in your mind. You have an integral, forget about that, but just remember you have this operator that works on V, and you remember we use a T to denote the fact that the volume may change. And then we consider T plus dt, etc., etc. And now just focus on the idea. The idea is, okay, this is the first step. The second step is to have a volume, so to speak, not conserved, I don't like to use this word, but like a constant. How you consider the volume a constant if it depends on time? Through the Jacobian. Through the Jacobian. So here, instead of dx, remember, you have the d3x, the volume. Instead of d3x, you want to convert x into x0, and so V becomes V0, but of course, the relationship between one another is through this. So somewhere here must must appear the Jacobian. And then the Jacobian is just a scalar quantity because it's the determinant of this transformation matrix. And so you use this scalar quantity in and out of your derivatives when you perform the kinematic transport theorem. So this at a certain point goes inside and then operates on this big capital G times J, etc., etc., and you can work out the result of the kinematic transport theorem because at the very end of your passages, you will have this J and X0 again. So you recover X as function of, in terms of the volume V at the time t. And the operation to go from 0 to time t is done by this Jacobian. So this is often the case in many situations that may be useful to remember. All right, so I want to just summarize what we had so far. Yes? Yeah?
Before you just swipe out all the stuff there, can you just give more words about that blackboard, the final formula? Does that mean...
That one?
Yes.
Yes.
So U is dot U...
Yes, this is the normal. So here is S is just the boundary of the volume.
Yeah. So
and then...
Chi is what?
This is just a potential.
Yeah.
And this is the sum of these two potentials. And you may take a reference potential at infinity so that these two cancel. Two cancel if you consider the infinite domain. So this is the case for a finite volume or for an infinite volume. If you take an infinite volume, then of course S is, so to speak, at infinity, and this chi takes the value of chi infinity. So this cancels out. If it is the volume is finite, then of course again chi is the value at the boundary. And because you have this going from from a volume integral to the surface integral, you arrange that way. Otherwise, if you drop this condition, you can still, of course, use it. You can still consider conservation of kinetic energy under a general fluid.
So that means in your lemma, you have three statements there.
Yeah.
Maybe you have the fourth one, which just have your statement there. You can just make some transformation of your formula to... Sure, yes. This is often done, in many cases, is done just to, it's a short course, and the idea is to focus on the very fundamental aspects. And applying this transport theorem and the other tools, you can reformulate the same ideas as is done here. Many ways, different ways. This is why. Well, because people during the centuries and during the years worked on one aspect and then the other, and now we can grab different things under the same umbrella, so to speak. So this is just equivalent, saying one or the other. But to find these links, of course, occur during time. Yes, so you could include. Let me be now. I cannot. It's just a speculation. But a long comment of having equivalent statements for the same thing. One wonders, you can think of the Noether theorem to derive conservation laws. You can think of structure that have a rigid mathematical structure that give conservation laws. So if I think of integrable system, I'm not considering integrable systems here because this is a big question. It's a big question of mathematics. If Euler equations are integrable, is another way, equivalent way, to say if there is a singularity in finite time of the Euler equation. The famous problem I mentioned yesterday is exactly the same thing. If you prove that a system is integrable, then evidently you don't have singularities, and so you get your $1 million Clay Institute prize. Now, integrability would mean that we have many conservation laws, not only the three. We struggle with these three. But we have Hamiltonian systems that give us Casimirs. Many, infinitely many. Infinitely many. Infinitely many is more than 3 and 4. So, and this helps me to remark again what I just mentioned at the beginning. So that is quite astonishing to see that helicity was introduced only 60 years ago, considering the work on fluids, at least, which has a 200 years history. So you wonder, maybe there are other important conserved quantity, other important in physics, other quantities that are important in physics that are still to be uncovered. One day, maybe, you can state each of these conservation laws in terms of others, or maybe not. One would like not, would like to have them really independent one another. So conservation of mass, to some extent, is independent to conservation of linear momentum. I'm more hesitant to say that it's totally independent from conservation of energy, because we know the trick in going from mass to energy. So you see, this is the business of unifying theories in science. All right. So in order to complete this, I won't write it. It's not so important anyway. It's written in the notes. Remember, you have two sets of equations. One is ideal fluid mechanics, Euler equations, and the other one is with dissipative effects. And this is referred to as Navier-Stokes equations. In order to use this set, you can complement this set with one more condition, incompressibility, or not. So either you include the divergence-free condition or not, and the boundary conditions. And boundary conditions are typically posed according to the problem you study. So if the fluid is in an infinite domain or it is in a finite domain, and according to the velocity at the boundary, if the velocity at the boundary has, is a flux through, or it is zero at the boundary. So if it is a solid boundary, then typically you prescribe velocity equals 0. And the normal component, of course, 0. And prescribing velocity on the boundary is what gives you a chance to select the appropriate solutions. All right, so we stop here as far as these introductory questions and material, and we move to vortex dynamics. So my point is today to focus on vortex dynamics, and tomorrow on magnetohydrodynamics. Because, of course, here one of the forces can be the Lorentz force due to the magnetic field. Again, I anticipate in magnetohydrodynamics we consider an ideal case again when viscosity is 0 and the fluid is neutrally charged, so that we can reduce the Maxwell equation to the so-called ideal magnetohydrodynamics equation. We will see it tomorrow. But for the moment, let me focus on vortex dynamics. So we introduced the concept of vorticity yesterday, and we talked already about the circulation computed on a closed loop. So clearly these concepts come useful when we want to talk about the fundamental laws of vortex dynamics. Again, I'll be rather brief on the fundamental equations. There is one derivation in particular that takes time, so I cannot do it, but is important, and so you will have it in the notes. So as I mentioned yesterday, the work on vortex dynamics has a beginner, and the beginner is Helmholtz. And Helmholtz was in Göttingen at the time when the younger Riemann was. And Helmholtz gave already many important contributions to a number of subjects in science. And one wonders, I wondered at a certain point why I was taken by vortex dynamics when I was your age, and I liked it a lot, and I wanted to understand at a certain point, I'm curious, I suggest you to be curious on science, on history of science, because you discover some simple things that allow you to understand how ideas develop. When sometimes you have bad experience at school, you remember maybe some bad teacher that tells you, this guy did this, this is obvious. And then it's very difficult for you to understand. And you start thinking how this guy came up with this demonstration or this out of scratch. Impossible. Don't believe it. It's impossible, except very, very few cases maybe. But it's impossible. It cannot come out from nothing. It must come from something. So Helmholtz, why Helmholtz was interested in vortex dynamics? Oh, everybody was interested in vortex dynamics. You see the pictures of water swirl, of water edges, of water vortices in Leonardo da Vinci and in the Greek mythology. So everybody thought and dreamed about this, so it's not a big wonder. But why he was so keen? At a certain point, he was interested in the production of music. Organ music. And organs have these cans and these tubes, long tubes, they produce sound. And then he was interested how this sound, the difference in sound, was related to the construction of these tubes and the function, of this instrument. And then studying this, he noticed that the air that was pushed out to produce this sound was kind of forming vortex rings. If you think of smoke, you can visualize these vortex rings. And then at a certain point, he became more and more interested in that, and he wrote a paper, famous paper, 1858, on conservation laws. So much work was done after that. I told you yesterday that that was considered a risky business. It's written by him on the first page. The mathematical community of the time was rather, not skeptical, but was a little bit afraid to work on that topic because of possible singularities associated with velocity, etc., as they were a bit scared to work with dissipation, viscous fluids, etc., Although they recognize the importance, of course, of these concepts. So in order to get there, I need to introduce 2 or 3 basic definitions, and one of them is circulation. So we already said it yesterday. Definition of circulation is the following. Circulation gamma. In general, we may think of gamma as function of t of a vector field. It will be the velocity in a moment, u, along a simple closed curve. Remember, closed curve in mathematics is called circuit. Simple in mathematics means no self-intersections, okay? No self-intersection. The business of self-intersection of a curve leads you to the problem of identifying the tangent to the curve in one direction or in the other, so you avoid that. Although it's getting important in graph theory, etc., etc. So nowadays we are revising so many aspects we consider taboo. Okay, in R3, so this is our curve C in R3. And everything is obviously given by this. Gamma t is just the integral closed ct of u dl, where L is just a
denoting the position vector on this curve. Okay, so we can think of a parameter on this curve and consider this as the integral of u in terms of this parameter s, let's say arc length, dl with respect to an s, ds in ds. Okay, so this is arc length, if you like. If it is arc length, there is no need to specify the domain of integration because it's a closed curve. So we go from any point to any other point in order to close the integral. Okay, so we have the following theorem. So this is, let me call it, let's give it a name, a kinematic transport of circulation, because we want to prove something about circulation, and I have to focus a little bit on this because circulation plays an important role in. Yesterday we mentioned multiply connected domains, and the circulation can get to 0 or not according to the multiplicity of the domain of definition. Okay, so we want first to prove this result, i.e. that d dt of this quantity Ct, udl, is equal to the integral on du dt dl. Okay? This is, of course, related to the transport theorem we saw before. Okay, the proof is simple if you reconsider circulation in terms of arc length. So in terms of arc length, dl becomes, so this by definition, dx on ds along the arc length ds. And we may take s arc length exactly. Before I said it can be arc length, it can be a parameter on the curve, but if we take arc length exactly, then dx ds, if x becomes function of arc length, then dx ds is just the unit tangent. Unit tangent to c in ds. Okay, t, unit tangent to c. All right, so we have d dt, integral, the c, udl. We transform that, d dt, integral, c, in dx dt, dx ds, in ds, dx dt being the velocity, and this is integral on c of, we go inside that and we have d2 x dt squared dx ds plus dx dt times the derivative with respect to time of dx ds. All this in ds. Okay. All right. So this is the integral c du dt. Dx ds is the tangent, so we have the unit tangent plus u dx dt plus u dot dds dt ds exchange in this case, and for those of you who like general relativity, etc., you have to consider cases when you can do this or cases where you cannot do this. So it's interesting because when you cannot do this, you have to introduce a tensor, a torsion tensor, that takes into account the connection. Not always you can do this exchange, but anyway, R3 Euclidean space, you can do it. And so we are here. Sorry, I lost track.
is dds, okay, of dx dt in ds, and this is the integral du dt times unit tangent plus u dot du ds in ds. Okay? Right. Last line. This is integral du dt along tangent plus, now this term, you can recognize here dds is just the gradient of u along the tangent. So let me write it like u dot grad, intending for this along the tangent. I would say along S, right? But I specify this by putting a T here in ds. We have a T and a T, so this is just the integral of du dt times the unit tangent in ds. So we can reduce this back to the L. TDS is just dl, so is just this du dt times dl. Okay, so this is, as far as is concerned, this derivative to bring in or out this derivative. And since this can be brought in, and we have du dt, you remember immediately we deal with Euler equations. So we have obviously the result of Kelvin circulations. And this is d dt of gamma t equals 0. That means that gamma is constant. Okay, so this is obviously an exercise once we know the equations. Integral du dt in dl. And this is, oh sorry, I just missed what I wanted to, d dt to prove of gamma t is this. And this is just minus, I substitute the Euler equations there, C 1 over rho grad P. And this is a closed curve, so the gradient of a closed curve is just 0. The integral of the gradient on a closed curve is just 0. Right. So this is the statement that under Euler equation we have this other conservation law. Circulation is conserved. Again, sometimes I go back, my mind goes back to history of science, and so this law, so this is I don't know, I can't remember, I'm sorry, but I'm tempted to say something like 1869. 1869. But Cauchy, Cauchy knew this. Cauchy knew this. It is not exactly, of course, the same derivation. Cauchy knew that circulation had to be constant. So it anticipated Kelvin's theorem. And it was this observation is in the middle of other results, and it wasn't really so interesting. because the Academy of Paris set a prize for a certain aspect, and this was not the central aspect. So this result of Cauchy remained unknown. And I knew it from my university teachers, but I noticed that nobody knew that, especially when I was in Cambridge. And it's quite remarkable that an in-depth reconstruction of this work was done and published only very recently, a few years back, by Uriel Frisch. Frisch has been a director of the Observatoire in Nice, observatory, and is a great expert in turbulence. And Barbara Villone, she is in Torino. Anyway, and they reconstructed the history at the time of Cauchy and found remarkable aspects. I will say something else about Cauchy because, as I said, I learned it from my school years, so to speak, my undergraduate courses in Torino. I'm indebted for this to Professor Germano, who I don't know how he knew about that, but this is went lost in books. So you don't find a reference to Cauchy almost at all in books, and certainly not about Kelvin circulations. Anyway, so Kelvin had this result, and I mentioned 1858, and now I'm going to write it down. 1858 is the year of Helmholtz. Helmholtz, 1858. Conservation's law. Conservation laws for vortex dynamics. Okay, so these and Cauchy worked on these laws, on the laws of vortex motion. That's why he found the circulation theorem, among other things. Anyway, the vorticity, yeah. Yes.
1 over rho and the gradient of P, the pressure, then you have to dot dl or something.
Ah, sure, sorry.
So, dl.
Yes.
Yeah. So that just means it is 0 because it is a circular integral.
Because it's closed.
Yeah. So after you just do the whole circle or just the root, then after one period you just return to the original place. So that is 0.
That's right.
And even C is a knot.
Ah. So, yes. I smile because this is the question I posed to Keith Moffat when I was in Cambridge, his student at the very beginning, when we met. I asked him, what about C? If C, for example, if C, suppose you have a field line, and suppose you go around a number of times, many times, and then you close the curve on itself. How about that?
C is a curve. You choose.
Yes, we for simplicity we take it simple, closed curve, unknotted, unlinked, etc., etc., etc. Clearly, if you go many times around before closing itself, you have to count the contribution of the field through the surface many times. So you have a linking number. You are anticipating what I'm going to say in 2 days' time. You have a linking number that comes up. Yeah.
So here is something C to be attributed to yourself.
Yes, yes. Is a good point, this, to have a curve that is topologically complex, so to speak, or that wanders, that goes around twice it may be topologically simple, but linking non-trivially with the field line, that you end up with a topological contribution to this result. It's interesting because you may have, you remember certainly yesterday when we talked about the pillar in the fluid flow, and then I said, okay, let's do this exercise now. We remove the pillar, but we keep in mind that there is a hole in space, in the fluid domain. And the circulation around a potential flow yesterday could go to zero, right? The circulation, you could shrink to zero that. But if there is a pillar or is a hole in the fluid domain, you cannot shrink to zero circulation. So circulation, which is a measure, if you like, of the fact that you can go with a field line around a closed circuit, is also a measure of the obstacles that you have in the domain. And if these obstacles are not pillars, but are holes, in other words, if the fluid domain or the ambient fluid is multiply connected, then you have to deal with circulations that are measuring this connectedness. Because you cannot, you can go, suppose you have a hole here, okay, so the circulation here is 0, is 0, is 0, but here is not 0. And suppose there is another hole here that is much bigger, then you have to take account of these two holes, etc., etc., etc. Right? But then you know, I'm not going probably, I'm just mentioning it, you surely know Stokes' theorem. Stokes' theorem I'm going to say it in a moment, I'm just anticipating what I'm saying, is circulation and flux. Circulation and flux are the same thing. And indeed, you now start thinking that this pillar of concrete that is in the fluid maybe is represented by a vortex tube that is coming out of the blackboard. And why is the analogy with the pillar? But the analogy is that water is water and concrete is concrete. And what about vorticity? Well, here is irrotational and here is rotational. Here the curl is different from 0 and here the curl is 0. We cannot mix the two unless we resort to dissipation and diffusion, etc., etc. Then, of course, we know that the two mix. But if we keep separate these worlds, then this is irrotational, this is rotational. And now I do another jump, a little step, not a jump. And for those of you who are keen, I'm sure there are some keen on defects in quantum fluids, say a Bose-Einstein condensate has a defect, and this defect is this pillar. And this is the vortex, the quantum vortex that we mentioned yesterday. Is a vortex, but is in the context of GPEs and hydrodynamical interpretation of Gross-Pitayevsky equation through Madelung transform, 1927. Madelung proposed to interpret, I have no time to go into that, but this is very interesting. Madelung proposed to interpret this wave function that troubled so much some of the people of the time, for example, Einstein, and proposed a fluid dynamical interpretation of the wave function. And taking the amplitude of psi equal a density of a fluid-like system, and taking the action, you have, I'm just moving to another topic, but you have psi. You take psi as rho, square root of rho e to I to say the action, you would say, S, right? And this S, the grad of S, you call it U. So you have a velocity field for a fluid-like system and the density for a fluid-like system. This is due to Madelung. 1927. And through the Madelung transformation, the GPE, I should talk about this. GPE, maybe. GPE is a nonlinear Schrödinger equation, right? It's a type of nonlinear Schrödinger equation under certain assumption for a dilute gas, etc., etc. And then under this transformation, you can decouple there is an I here. You can decouple real and imaginary parts from the nonlinear Schrödinger equation of psi, and then you derive the continuity equation of a fluid, and almost like a Navier-Stokes equation of a fluid that has this density, and this velocity. So it's a kind of abstract. It's very interesting because it was done in the 27, and then somehow resuscitated by a Japanese scientist much later in the 50s. And for all those years, until the 90s, this stayed there. Not many cared about, etc. But then came superfluids first, and then all these results in modern material science, and then the condensates. And with the condensates, people could put in a computer fluid dynamics and see how fluid dynamics of that type generates or not vortices. And these vortices are quantum vortices. So we're talking about extremely small scale fluid mechanics. Indeed, it's not really fluid mechanics, literally speaking. It's a gas of bosons. It's a gas of bosons that behaves like a fluid continuum. It's not, of course, a fluid continuum. Okay, so these defects, now this is the cross-section of a defect, of a quantum vortex. Maybe this is an Armstrong unit, and maybe it's long, I don't know, a few millimeters. So it's a defect in a so to speak, continuum system. And of course, the circulation is different from zero, because it cannot be shrunk to zero. So if we think of a vorticity as a flux going through, then circulation through Stokes' theorem becomes a measure of the flux. So circulation that detects topological complexity, because detects the number of holes that are in the fluid domain, becomes also a physical measure. That's why it survived in quantum mechanics, as you know, with the name of topological charge. You find in papers topological charge quite adaptly, quite correctly. It's just circulation. And it happened to me a number of times to just point out to people that is the same thing. Or there are works. There are work, sometimes we publish sort of rubbish. There are people trying to, they do a lot of work just to produce the fact that the circulation is conserved under certain conditions in the context of quantum field theory. Well, okay. All right. So this is it. Helmholtz. So we are now ready, because I mentioned Stokes' theorem, which, by the way, just because we're chatting on history, apparently, if I remember correctly, is not strictly due to Stokes. I think Stokes gave us an exercise to a student, and then when he realized there was what we call Stokes' theorem, he lost track of the student. So some time passed, and they wanted to find out who was this student. So Stokes' theorem is actually due to a student of Stokes, if I remember correctly. Please excuse me if I'm wrong in certain quotations, because I didn't prepare. I talk out of... all right. I think it's correct. Anyway, Helmholtz. So this paper is a great paper, but I have it's impossible in a few minutes. Oh, actually, it's possible, but I don't want to do it because I would be too quick. So I just state the result. So one result is the equations. And the equations are say vorticity, transport equations or theorem, and for isentropic or isentropic flow, so ideal, no exchange of ETH, etc. We have the following equation, d dt of, in general, omega over rho. We can relax rho. We can say that rho is constant, okay? But for the moment, let me write it like this. And this is just the transport omega over rho of along the grad u. Well, I have no time to prove this, but in the course of the proof, we find the following equation, and this equation is so nice and useful that I have to mention it. We find the induction. The induction law for vorticity. In deriving this, at a certain point, you know, we start from Euler equations and we take the curl, etc., etc. We need the curl. So the first steps are easy. You take the equation, you take the curl goes on U, so you work out omega, and then you do a few passages, and you get to this, d omega dt equal the curl of U, well, let me use the wedge here, it's just easier, omega. And then you keep going. You keep going, and then you get to this one. You know, this one is just this is just a piece inside here. And you see this equation. That equation, for those of you who are at home with magnetic fields, should suggest something, because as we will see tomorrow, if we put B, magnetic field, here, and here, I'll show you very briefly tomorrow, we get to Faraday's equation. It's Faraday's equation. So this is the transport of omega. But this equation is different from Faraday's equation in at least one respect, is that here, for Faraday, we have a velocity of the fluid and a magnetic field. The two don't talk to each other to some extent. Magnetic field is magnetic field, and velocity is just normal fluid particles moving. And they transport, the fluid transport the magnetic field. So, like if it were a scalar, like a powder. Of course, it reacts on the fluid, yes. But, you know, ideally, it's just transported by the fluid. Then it reacts with charged particles, yes. But if the fluid is neutrally charged, then it's transported. But here is a different story, because the change of time in time of omega is related to U. Indeed, omega is the curl of U. So this is nonlinear, highly nonlinear, and that's why it's so difficult to understand. We read it, but in order to compute omega, we need to have U that is related to the curl. And so the two talk to each other. That's a big difference with the Faraday's equation. So formally is the same two equations, but the substance here is quite different, is that U and omega are related. In that case, U and B are not related. So in a sense, there is a simpler situation. All right. So let me see if before maybe coming to something else, so this is important. I'd like to emphasize the role of coherent structures. Again, this is simple. Coherent structures are field lines, like magnetic field lines, like streamlines, or field lines, vorticity lines, that stay together, localized in space. And this is not so abstract. It's obvious. If we have a tornado, we see that the rotational region is confined, not as neatly as I intended here, of course, because it's real fluid, there is dissipation, etc., but is rather confined. And sometimes these tornadoes come thin, and that means very intense. We will see from Helmholtz's laws the relationship between intensity and size, so to speak, of this region. Because flux is conserved. I am anticipating, I'm using already concepts that you know. Circulation is conserved and is measured by that amount because it cannot shrink further. But then you use Stokes, and the circulation of U around this circuit gives you the flux of this quantity going along normally to the board, and the flux is related to the surface. And if the flux is conserved because circulation is conserved, because the two things are the same by Stokes, then if you squeeze this surface, the intensity has to increase the other way around. If you enlarge this, intensity goes down. And this is, I'm anticipating the third discovery of Helmholtz. Helmholtz proved this without knowing Kelvin and Stokes. One was in Germany, and the other, Stokes and Kelvin, were in Great Britain. All right. So if we consider localized distribution of field lines, then we can start doing some interesting things. But this is a rather recent point of view. It's remarkable because for us it seems natural. But until, say, the 50s, 60s, 1960s, quite recent years, people didn't focus too much on structures, on vortices, on localized vortices. If you go in, 1900, you open the book of maybe Villa, Théorie des tourbillons, was a major topic in Paris at the time, is made of point vortices in a plane. It's again fashionable because in meteorology, you can think of a sphere with vortices that are localized on points on a sphere. So it's not such an old topic that is no longer relevant. It is relevant, but the people didn't tackle the problem of three-dimensional distribution of vorticity. It was far too difficult. And then people in the 50s and 60s started to notice that turbulence is made of structures that are interacting. And this was, again, in the mind of the people, but at a certain point computers came along and could perform very, very sophisticated numerical simulations of Navier-Stokes. And in Navier-Stokes, real fluids, you see the role of these vortices. So vortices are just the localized tubes of vorticity. Imagine in R3 that you have a tube, and on this tube you have field lines here. And these field lines are filling these tubes, and you may say that there is a region that, of course, is difficult to identify exactly, but there is a region where vorticity is dominant, and the region nearby where vorticity is basically negligible. So again, in an ideal sense, you can identify a vortex tube, and the vortex tube has its own axis, of course, and you can follow the vortex tube in the fluid, and this vortex tube can interact with other vortex tubes. Then two other important facts. One is that people started to visualize structures, fields, not only in turbulence, but, for example, observing the solar corona, the sun. And the sun, 90% of the energy emitted from the sun to us in all forms is due to the interaction, breaking of flux tubes, well, let me say arrogantly, of magnetic field. And if you are keen on particle physics, you will object to this statement, so I will say, to accommodate friends, of plasma. Plasma. But this plasma is captured by magnetic fields. And as we cannot see magnetic field, we cannot see vortex lines. These are mathematical inventions. A vortex line does not exist. You see powder that is spiraling about a vortex line. And what is the center of the vortex line? Well, maybe in the simplest situation is a low pressure, So it's spiraling because it's captured by low pressure. But if you measure the curl is different from zero. So you can model, you can make a mathematical model and thinking that a tube is made by these vortex lines. Remember, you do not see vorticity and you do not see magnetic fields. But you can compute the effects of their presence. For example, plasma particles are captured, there's a Larmor radius, and they are captured by the intensity of this magnetic field. All right, and so we can model these structures. And when they started to observe with the finer instruments the solar corona, they noticed the structure of these gigantic loops, these magnetic plasma loops. And I remember when I was a bit older than you, at the age of 30, I gave a talk, my first talk in Italy, I was in England, and my first talk in Italy was in Pisa, at the Scuola Normale, and I had a seminar with a theoretical physicist. And somebody from the Observatoire de Meudon observatory, in a very important observatory in Paris, I mentioned these loops, and he objected. He was totally, he said, but these plasma loops, these loops are plasma. Don't talk about magnetic field lines. Magnetic field does not exist. And he is a plasma physicist. And I wasn't surprised at all, because again, history helped me. History helps. When Alphen found a way to describe the velocity of waves on magnetic fields, in his mind, he referred to the work of Faraday. Faraday described magnetic field lines as behaving like elastic bands. And this is an analogy, but he told this to the wrong person. He told this to Fermi. He went to Fermi in Chicago and he told that he could derive the velocity of the perturbation of magnetic field line with a formula, and he gave the formula, and we all know the formula now is Alphen velocity. And Fermi said, well, I don't trust this. I don't understand. Fermi was a particle physicist, and he couldn't follow very much these ideas. He wanted to prove based on particles. And he took, at the time, a boat back to Sweden. And when he was at home, after a few weeks, he received a postcard from Fermi. And the postcard is a famous postcard with just a writing, "You are right!" exclamation point. We don't know how Fermi derived, if he derived the same equation in terms of fields, probably not, but this is the story. So when I was told about these magnetic fields, I knew about that. But I was, so to speak, I was happy that somebody had different ideas to confront with. And after a few years, now the business is totally settled. They observe with incredible precision these structures. Of course, you don't see magnetic fields, but these plasma loops are highly, highly localized, exactly as we do in modeling. I invite you all to go on the internet to check on this solar corona. You just type some keywords like, I don't know, solar braids. They form a braid pattern on the corona, and you can see the structure. And the structure can be analyzed in great detail, as we analyze structures and vortices. And the third strand came from superfluids. I mentioned classical vortices, magnetic flux tubes in the solar corona, and superfluids. Superfluids, same thing. Simulations came, and they started to look for structures, and now they see turbulence of these structures. But in superfluids, it's an easy life for me, because we go back to defects. These are really defects. Here, there is a problem to define where the fluid is vortical and where is not vortical in real fluid. But for defects or for superfluid quantum vortices is extremely precise. There is a place in space where vorticity is there. And there is a place an Armstrong away where it's not there. Full stop. So it's very, very clear. Indeed, it's so localized that you use a delta function to describe these defects. Whereas here, I'm going to use, or I'm not going to use in this lecture, but people use just classical analysis. You integrate over something, over a domain of what? Of a function. What kind of function? Well, generally, you assume that here is a Gaussian distribution. And for simplicity, you take your vorticity as a top hat distribution. Here is vorticity, here is 0. And then in modeling real fluid, you say, okay, this top hat distribution gets to be smoothed out by dissipative effects. All right, so we deal with these structures now. These structures are very important. Remember, I told you so much energy comes from the localization of magnetic fields. So much energy is a Nature paper of 96 or something like that by Bernie Roberts in St. Andrews and somebody else. So is now a quite established fact, despite our friends in Meudon. And in Meudon now they work a lot about the simulation of magnetic flux tubes. Anyway, so we deal with these structures. And now the step is close to say, what about if these structures form knots and link? They form knots and links. Well, the easiest possible structure that we may meet is a vortex ring. And this was produced by Tate, because Kelvin wanted tabulate knots, and the starting point was the unknot. The unknot is just a torus. It's just a torus, and so he asked Tate to produce a vortex ring. And the vortex ring is just, you probably all know this, who is smoking is probably able to produce a smoke vortex ring. There are beautiful smoke rings produced by nature, for example, by tornadoes, and by volcanoes. And there are people hunting volcanic activity in order to take picture of vortex rings. These are not really smoke rings, are vapor rings, and of course in movies they don't shoot real bombs, but when they shoot or simulate a bomb, then you see a vortex ring producing, because it's a big puff of air that is, plus sound, that simulate this. And then there are, of course, the results of bombing, of more serious bombing, the atomic bomb, etc., where a gigantic vortex ring is produced. Now, this is a structure that is basically given by taking these vortex lines and putting them in a torus, filling the torus with vortex lines, and then thinking how it moves, and so to derive the motion of a vortex structure. And this can be thin or can be thick. If it is thin, is a vortex filament. If it is thick, is a thick vortex ring. And of course, the information of the velocity, etc., etc. I take the opportunity, since I'm just not writing, to tell you something else now. Of course, I appeal to your imagination a little bit. I have no time to go into details about that. But you notice here, this induction law is formally exactly the same as Faraday's law for magnetic field. And this analogy will carry on tomorrow when I will present two analogies, one perfect, one non-perfect, between these worlds. One is classical fluid mechanics, the other is magnetohydrodynamics. Why I'm saying this? I'm saying this because if you think of a vortex ring, there is an analogous structure. It would be what we call it. Maybe we can call it a magnetic ring, something like that, in analogy. But we know about something that is toroidal in shape that has magnetic fields inside. Is a tokamak. A tokamak. So these machines that are projected to, designed to produce energy from fusion physics. And the cross-section of a tokamak is not really, you know, a torus has a cross-section. You may think of a torus like this, with a cross-section circular, but this is not quite nature wants. What nature wants, you want a steady solution. You want a steady solution, no dependence on time, on the distribution of the field. So suppose here you have vorticity. Vorticity going round and forming a vortex torus. Then what kind of cross-section you would have? You remember we mentioned this problem yesterday when I talked about Biot-Savart law. Biot-Savart law is a domain of integration, and the domain of integration is the domain of definition of vorticity, right? But either we impose it, or nature is satisfied by a particular domain. If we impose it, it's because we have to do some mathematics. So one way to impose it is simply saying, okay, my domain of integration is a circle. And I use circular, you know, polar coordinates, blah, blah, blah. I do my integration, etc. And this is one thing. But the other thing is to see if the result I get is consistent with nature. And is not consistent with nature, and that was a big business in vortex dynamics. Actually, was one of the core topics that pushed vortex dynamics to be tackled by great mathematicians, because there is, in Biot-Savart, there is this relation. I define vorticity, and then I impose somehow the domain of vorticity. But the result of it is a velocity field. And the velocity field outside is interacting with inside through this. So the problem is that my equation, which is an integral equation, Biot-Savart, remember, integral on the domain of vorticity, is an integral equation that depends the result u, the velocity, is related through the curl to what is inside, and makes this equation terrible. In other words, you should iterate what in computer you do. You iterate. You suppose one domain of definition, say circular, you get a u, you calculate the curl of u, you see how the curl of u that you calculate out of Biot-Savart is close to the vorticity, the omega you asked to be in that region. And if it is not, you modify a little bit, you modify a little bit, and you modify a little bit, and you discover that this cross-section is not at all circular, is a D shape. And this D shape, and there are, of course, all inside, all the structures is a bit eccentric, so the eccentricity goes towards the center, and the D shape is the exact result of a steady problem. And the steady problem is the vortex ring problem that has been studied by Kelvin. Kelvin, of course, assumed a thin vortex ring, so he was safe in saying that the cross-section, we can neglect the cross-section to be non-circular. We can take it as circular. And it will be maybe not so quite correct, but it's thin. It's thin, the vortex. So we can get rid of problems. But if it's thick, then it's not circular at all. And from Kelvin, people worked on that till recent time. And the other guys on Tokamaks worked on the same problem. So in one case, you find a steady solution for the vortex ring. In the other case, you find a steady solution for the tokamak, which is called Grad-Shafranov equation. And the Grad-Shafranov equation is exactly the analogous situation of a steady vortex ring in vortex dynamics. So when you look at the tokamak and you look at the structure here, how it is made, you understand very well how is the structure of a vortex ring. Of course, in laboratory, they did experiment, etc., etc. So this is the analogy that carries through and helps us to understand many things, because, as I said, here the difficulty is related to the relationship between U and omega. There is less difficult, so we will move to magnetic fields because it's easier to do work. And by analogy, read out, if we can, something about vortex dynamics. But I put Helmholtz there. I have to give you one more statement, and is about the conservation laws of Helmholtz. Two contributions. One is the transport equation, and the other is the conservation laws for vortex dynamics. We'll do it in the second part of today. So I stop here for the moment. Okay.